Welcome. Welcome to this webinar. How much can the Superscanner unlock for the battery industry? We're happy to have you here. We have planned for about half an hour of sharing, and then we follow with questions and answers. And if we would not manage to respond to the questions in here, we will come back to you separately and directly. My name is David. I'm the CEO at Excillum.
Yeah, hello, I'm Bernard, and I'm the head of VCbattery.
And my name is Eric, and I'm a co-founder and the CEO at Glimpse. So I have the honor of kicking us off. Just one slide to warm us up. Essentially, we wanted to spend a little bit of time to sort of contextualize the webinar today. We're going to talk about Gigafactories economics, and obviously the first thing that comes to mind is cost and performance. I think it's on most people's mind. How do I run my factory cost efficiently, and how do I maximize the performance of my battery cells? And those often come with a trade-off. So for instance, I'm sharing a couple examples here. You can introduce lower cost raw materials that will improve your cost, but make your performance worse. There are things you can do that will improve both cost and performance. So for instance, you could have tighter design margins, so you can essentially improve your dollar per kilowatt hour and improve your performance by increasing your energy density. And then you can have things that makes your cost worse, so increase the cost of your cell, but makes your performance better, right? So folks are generally pretty familiar with the different trade-offs between cost and performance. And I think the key message today is quality is just another very important variable in this equation, and there are trade-offs between quality and cost on one hand and quality and performance on the other. So using the same examples, you can see here that things that make cost better oftentimes make quality worse, and things that improve performance also typically or sometimes make quality worse. And so because there are trade-offs between those three factors, the question is this always a zero-sum game? Do I always have to have worse performance when I reduce my cost and improve my quality, or better quality comes at the expense of performance and cost position? And obviously, we're all familiar with why the answer is no, is through innovation, right? And so you can, for instance, introduce better raw materials that are potentially less expensive to produce, have better performance in your cell, and improve your quality overall. You can also have better processes where, for instance, processes that help you improve the throughput of your factory, hence reduce cost, improve performance of the battery cell by better control, less variation, and as a result, improve quality. But for quality, there's a third thing that is sometimes missed or not discussed, and it's better QC technologies. So the ability to inspect inline your battery cells and have real-time feedback in your factory has a positive impact on quality, and as we'll see today, cost and performance as well. And we're going to talk about what we think is the most exciting inspection technology that has been introduced in the past few years, even potentially a couple decades, and that's high throughput inline X-ray CT scanning. So the ability to scan entire battery cells with X-ray and extract dozens of features from those scans, all of that in real time. So that's what today's presentation is about. And we wanted to remind everyone that it's not just to improve quality, but it's also to reduce cost and improve performance. And we'll see that in the next few slides.
Oh, thanks, Eric. These are complex challenges, and also there's huge potential. When you reached out to us some 2 years ago, we knew that our X-ray source is a great fit for imaging of batteries because of material characteristics. So, and for more than 15 years, we've pushed physics limits, and we've designed and we've engineered and we industrialized. So since years now, our sources not only run in labs, but they run in fabs 24/7, typically in semiconductor, electronics, and battery applications. So our people and the investments levels that we have make us a world leader in microfocus X-ray technology and helps us put the world's brightest microfocus source on the market. But this is what we do. But what it really brings to anyone else is more speed and better resolution. So these are the values that we can add. Then when we look at the market, and especially the cell maker or the cell buyer market, there's plenty of players that look for improvements and care a lot about safety, hence also their brands. No one wants recalls, a lot of costs associated to that. Everyone wants an effective manufacturing process and high yields. So these are things on their minds. And many of the leading brands of cell makers or automakers have been at our site in Stockholm. They bring samples, they test their cells, and they learn from it. And that's all good, but it will not impact their manufacturing process, really. So whilst they have a need in the manufacturing process, which you guys at Glimpse had realized, we want to help them at scale. But of course, we sit on the source, which is a great enabler, and it's a bottleneck that needs to be removed. But when it came to us, we needed something more. We needed a machine that delivers all the data for your software at Glimpse. So we took you, Eric. We took you to VC Consult and to Bernard at VCbattery. So the question arises: if we are to make a change in manufacturing, what would it require? What were the main challenges to actually create a system that can manage at these speeds? Bernard, what were the challenges?
Yeah, very good question. So really, when we started developing the Superscanner, our VCB2 here, having your outstanding X-ray source was really the foundation. Yeah, the real challenge then started because then we had to transform this into a fully integrated high-performance system that delivers both then speed and precision. So around your Excillum X-ray source, we built a high-speed imaging chain, including photon counting detectors. Both together were able to generate enormous 3D data volumes in highest speed. So this was the basis. Yeah. But then to handle all this data in the fastest time, then we had to develop ultra-fast data acquisition, ultra-fast data transfer because of the sheer massive amount of data again, and high-speed reconstruction pipelines. It's very important for us. And then this powered by algorithms, and then utilizing also high-performance computing. All this together made it possible that we can then at the end create true real-time 3D image processing without any compromise on image quality and resolution. So this was the one major part. The second major part was on top that we had developed a highly accurate parts handling, inclusive some really instant calibration functions. So we had to assure that we have a reliable and repeatable data generation. So that was the key asset for us we had to bring in. So we had experts from automation, metrology, high performance computing and software together to turn this complex technology and with several layers of new innovative technology stacks to turn it into a robust turnkey solution. So that was really our goal. And then optimizing it for industrial stability and reliability. So that's the result, is the fastest CT scanner. And on the video you are seeing right now, you can see the machine in operation under full intensity inspection. So the machine itself is capable to inspect up to 16 cells per minute based on a, for example, 4680 cell format. So this is a real remarkable throughput for high volume production. On top of that, we achieve a 25 micron resolution, which is really needed in this market to detect even the most demanding defects. So keep this in mind, it's very important for all customers here. So in every detail of this machine then has been designed for maximum measurement accuracy and repeatability. So this is, again, this is the outcome of our development work, a fully integrated high performance CT system. And if you want to have more information, I can only refer to our technical webinar for a deeper dive on that.
Wow, amazing, Bernard, and beautiful actually. So thank you. Eric, so now we have this machine. What does it really do for speed and quality of data?
Yeah, so we thought that instead of walking the audience through some images on a slide, we would give you a live demonstrations of those scans that were acquired on the portal. So I'll switch over my screen to the Glimpse portal, and we'll show you some actual scans that were produced on this machine a few weeks ago. So what you're looking at on my screen here is the Glimpse portal. You're in demo mode here. So we scan over 1,000 battery cells. Our customers get their data in private mode, and you're all allowed to create a login. Access takes a few seconds, and you can explore various cell form factors. So we got some 18650, some 2170, 4680, and then we have some prismatic and pouch cells as well. Not going to spend too much time on those. I did want to pull up one of the 35 scans that were produced on this machine. And one thing that's sort of groundbreaking and really important to understand here, each of the scans has been produced with a 10-second cycle time. And that's including loading and unloading into the cabinet. And those scans, you will see in a second, are full cell, right? So when you hear about inline CT scanning, you always want to be careful and ask, what's the image quality that was produced? Is this a corner of the cell, or is this the full cell? How big is the cell, right? And so the best way to answer those questions is to show the image, and so that's what we're doing here. So I'll turn off the computer vision algorithms for a second, and I'll give a quick overview on how this works. So here you're looking at a battery cell in 3 dimensions. Here I'm moving up and down the cell, and on the right I'm rotating the cell on its main axis. And I'm going to zoom in so you can see the image quality. So this is a 25 micron voxel size, full cell, 10-second cycle time scan, right? So this has never been done before. First time ever that you are able to produce such a high level of image quality in such a short amount of time. So I'm zooming in, and then we can take a look at the header of the cell where you have the overhang region, and you see how clear the image is. And obviously what we do here at Glimpse is we're also showing that we can extract a ton of information out of those scans, right? So these are just a few examples of our algorithms. You have core area, core circularity, you have the can thickness, can dent, and so on. And then on the right, your overhang, cathode width, and so on. So again, this is kind of a first in the industry. We're super excited to introduce that to the battery industry. One more thing I wanted to show is, because we're scanning so quickly, producing scans every few seconds, we have built so that the next layer of automation, which is basically turning any CT scanner into a production quality monitoring tool. So here you can see how you can track your production over time, and then find out outliers where you might see a data point that's out of spec, and you can very quickly go from those dashboards to the scan themselves, because each data point will point to the image from which it was extracted from.
This is fantastic, and the amount of data here and of course in short time acquired is great. Now we've been working together for 2 years, so you came very early to us and VisiConsult, and wanted to sort of invest in a Superscanner type machine. So why was that?
Yeah, it's a good question. For us, it's so yeah, I think we reached out to you guys a few days after starting the company, and then you introduced us to Bernard and the team at VisiConsult. And I mean, look, the mission statement of Glimpse is to enable battery quality at scale, right? And in order to do so, we think CT scanning is kind of the best way to do this. It's not the only technology, quality control technology you need inline. You need a whole suite of technology, but in our opinion, it's one of the most powerful out there. But obviously, in people's mind, this is a very slow lab instrument. It's not a production quality monitoring tool. And it is sort of considered the gold standard for looking inside your battery cells and evaluating your build quality, but it's typically done, offline, a few scans a day. And here what we're doing is we're producing a technology that's able to generate tens or thousands or tens of thousands of scans per day, and we see this as a big unlocker in the industry. The reason we came to you guys is because we thought, okay, what will it take to bring CT scanning from the lab to the factory floor? And one big bottleneck is obviously how bright the X-ray source is. So, knocking on Excillum's door was kind of obvious to us. But then the source is, as you mentioned, David, only a component, and you need to integrate this source into a system. And we were introduced to VisiConsult and their automation capabilities and their ability to turn components into a turnkey solution. And so the three of us working together felt very obvious from day one, because we each have our own specialty, and putting these together and working closely together would turn what honestly used to be a concept on paper 2 years ago to a fully production-ready turnkey system today.
Thanks. It's been a fantastic journey, actually. Now that we have the machine in place, so let's talk a bit about what it can help us with. So this is the value topic. So what about starting a little bit with recalls?
Yeah. So Bernard and I will walk you through a few slides to essentially give examples of how much value can this technology unlock for Gigafactories. And the list is not exhaustive here today, but these are sort of some of the recurring problems that Gigafactories face, and how inline CT scanning, real-time inline CT scanning can help either save costs or increase revenue. So the first one that often come to mind is recall, right? It's very top of mind for folks. It's very costly, often makes the headlines, unfortunately. And it's the idea that sometimes you have batteries being produced that carry defects, and you have large waves of those batteries that exit the factory, bleed through your factory, and then end up in vehicles or any other battery-powered devices. And I think the punchline here is those defective cells, they very often come in waves. What that means is that defects are not randomly distributed in your factory, right? They often occur because something went wrong in your Gigafactory. It could be a tool that's out of spec, hasn't been maintained. It could be a new shift, hasn't been properly trained. It could be a second source material that you're introducing on part of your line and that has unintended consequences on your process flow. And so you have large batches of defective cells that come from this particular point in time and space. And this means that you don't need to sample 100% of your production output, right? So with the current technology that we're introducing today, the Superscanner, you can achieve single digit, potentially double digit % in terms of sampling rate, maybe not 100%. But the point is, it doesn't really matter, because what you want to do is sample a significant portion of your output. Doesn't have to be every single cell, so that you catch those waves of defective cells and being able to react in real time. And really, those problems are going to happen every other day in your factory. And that's fine, that's expected, but you need to be able to react quickly. And we've seen examples where those defects were being produced, those cells with defects were being produced for weeks or months or even years on, right, before being detected. And so this technology allows you to catch those within hours, within minutes, and really go from data points to scans and implementing solutions real time. So Bernard will give you a more detailed scenario analysis in terms of how much value this can create for your factory. I'm just giving you one data point here. Assuming a Gigafactory of 10 gigawatt hour, an EV pack size of 65 kilowatt hour, and an average cost of pack failure, which is about $15,000. Again, that's not including reputational damage, potential safety hazards, related expenses, and so on. But by catching just half of those waves of defective cells, you can generate over 10 millions in savings per year, and those savings stem from avoided field failure costs.
So, and that I think I will take over So Eric was now already on the production field and the production side. I will now go out and I will move to the, once the cell has been delivered to the car OEMs, and we want to lead you through a higher level simulation about how to understand that how life cycle cell data storage really can reduce your recall related cost for cell manufacturers or the car makers who purchase them from the cell maker. So how is this possible? So now with the Superscanner, our VCB2, we can achieve scans that are 20, 50 times faster than before. So really only from now on, first time really in history, you can utilize life cycle scan data from the production floor. So before, this data was simply not available. You have to understand it was not available. So now we can use a quantity of real life cycle data for backtracing from the field. And once you have this data, you have no longer need to recall 100% of a cell batch installed in a vehicle. Yeah. Instead, and that's very important to understand, you can target only the specific percentage, maybe 5 to 20% of cells proven to be faulty, because you know exactly where and when the defect then has occurred. So this is very obvious then. And you take this from your stored life cycle data. And then we made the simulation about the potential savings. So again, we have here a 10 gigawatt factory as a sample factory, again, producing a 4680 cell, very typically with an average electric vehicle. And when you then look on a one recall per year, you can start to make your calculations. And the calculations start typically at the car. The repair cost or the whole handling of such an incident of a recall can be between 8 to 15,000 euro, depending on the nature and the severity of the issue, and of course on the type of the car. So that means even a single large-scale recall can have a real massive financial impact on the manufacturer. So when you look here at the numbers, you can see cost reduction opportunities between 10 to 25 or even 30 million euro per recall event. So only when recalling only a percentage of potential defective vehicles. It's very important to understand. Yeah. So yeah, please.
Yeah, Bernard chiming in here. I think this is a very profound point where you need a system of record, right? Because those recalls sometimes they happen weeks, months, or even years after the productions, the cells have been produced. And so having the ability to store for many years this gigantic amount of data allows you to react very quickly, God forbid, when you have a defect in the field, and you can understand the magnitude of that defect. Is it just one cell? Is it just one pack? Is it 1,000 pack? And react quickly and understand what the problem is and if the problem is still running in your factory, right?
Absolutely. So again, it's not just about quality control, it's about risk mitigation and financial protection. It's really important to understand. So any cell manufacturer who wants to reduce the scale of recalls is not only getting his profitability up, but also his reputation. I think it's very important extra value on the cell maker side. So this is another clear example how inline CT scanning can help our customers. And maybe if you go further, we look at another use case here. So coming back from the field, going back into the factory, onto the factory floor. So again, a key enabler is process monitoring. And Eric gave you one example, and we drove this example to a higher level discussion. And again, what is important to understand is with this Superscanner, it's the first time in history possible that we can generate data which are instantly available for you at the production line. And not only that you have it available, you can really react very fast, and you can improve your process stability and your quality. So, and when you then do this calculation math, again, on a 10 gigawatt scale factory with a typical cell of 4680, then you typically can really reach yield improvements between 1 to 10%. And the annual savings is then, of course, you can make the math is quite impressive. So here, when you look at the numbers, we talk about 5 to 60 million euros of savings. And of course, this depends on where you are as a maker of cells. Are you starting up? Then typically you have low yield rates, so you have a potential much higher gain and risk minimizing with doing this. When you have many years established production, still every single margin of yield improvement helps you to bring up the profitability of the whole factory. So again, it's not only a diagnostic tool to use to do this process monitoring, it's a strategic driver for production efficiency, yield improvement, and ultimately then for cost optimization. So it's helping the manufacturers to be smarter, to act faster, and make more profitable decisions. So that's the key of this technology.
Oh, so here we get the link from a bright X-ray source to the system and to the impact on the cell makers and the cell buyers. But if you're a cell maker, so how would you know that it's really worthwhile for you to invest in this type of machine?
Yeah, that's a very good question. So, of course, every cell maker has his own typical challenges in the production. So what we are normally suggesting is come to us, send us your cells, come with your cells to us. We know they're very secretive products, so come to us. We are scanning the products for you. We're running them through the Glimpse portal, and we give you your first insights on your specific cells, on your specific problems. And from that, ultimately, you will learn what you are gaining from this technology.
Wow, that's a nice invite for collaboration and working a bit together on the business case and what it can bring. It's really nice. So this was a little bit about recalls and the process monitoring. Eric, what else values could this unlock, the Superscanner?
Yeah, so two more examples before we wrap up and take questions. So the next one is around change control processes, something I've been involved quite a bit in my prior role. And so this is essentially about introducing new changes to your factory. This could be a design change, it could be a raw material change, it could be a process change. Anything that involves a change to your plan of record has to go through change control. And you often work at R&D and then pilot to test those changes. And the last step is typically running your actual production line with this change for a period of time. Could be minutes, could be hours, could be days, and producing a large enough sample of cells that include that change before you temporarily swap your line back to your current plan of record to give you time to perform this change control process offline, right? And so here you see you swap your line once to introduce the change, then a second time to revert to your plan of record, and then a third time to fully introduce this change once it's been validated. And the problem with offline change control, it's very expensive, it's very time consuming and very manual. So it can last a few days to a few weeks, and essentially you incur a lot of resources. The first bucket of lost resources is lost production time, because every time you swap your factory back and forth, you're going to lose production output. But also qualifying those cells takes a lot of time. You have to do a lot of manual teardown, a lot of manual reporting, run a lot of tests on those. And when you do the math, each change is going to cost you, anywhere between $100,000 to $500,000. And then depending on the maturity of your cell production factory, you might do anywhere between 5 and 20 of those changes a year. So that, amount to between $500,000 and $10 million a year just to validate those changes. And the reason is because when you introduce this change in the first place, you don't have a high degree of confidence that you're not introducing defect in your cells. And the beauty with inline real-time CT scanning is that you can significantly reduce the risk of introducing those changes by essentially getting real-time data of the build quality of whatever change was introduced. And so that allows you to first, reduce your sort of change control process from weeks to hours. And second, because it's a lower risk change and you have more visibility, more data into what it's doing to your battery cells, you don't have to swap your line back 2 more times, right? You can just keep running that new change, and you essentially get a live feed of digital teardown, right? And then automated reporting. And so that might not be a viable path for all of the changes that you introduce in the factory. Some of those changes might require some cycling data, which would be part of an offline change control process. But a lot of those changes, at least in my experience, if you have a real-time view of the inside of your battery, of the build quality of your battery, you can run those changes and simply continue to run your line this way without having to sort of swap it back to your current plan of record to give you some time. So this is a lot of value created there, a lot of cost saves, typically quality team time, design team time, production team, and so on. So that was one more example. I'll finish with last one, which goes a little more into the weeds. And just to remind of the first slide where we explained that cost, performance, and quality are all related. Here I'm going to give an example of a design change that essentially can improve your performance while maintaining your quality. And that's really only being made possible by real-time inline CT scanning. So some of you might be familiar with CpK, right? CpK is basically a measure of how good you are in your factory at producing those parts, how reliable and controlled your processes are. So here I'm taking an example of anode cathode overhang. As you know, you always want your anode cathode overhang, those little branches that are in blue here, to be positive. And with inline CT scanning, you're able to measure your overhangs throughout your cell, both at the top of the cell and the bottom of the cell. And when you extract the minimum overhang automatically, then you're able to plot this distribution of minimum overhang for a given batch of cell. And so here, this is an example distribution where you see your 6 sigma essentially lands about 150 microns above zero. What that means is, and obviously, each factory has different spec controls, spec limits, and so on. But this example shows that maybe your overhang design here has been too conservative, right? And you're too good at producing those cells, and you're leaving about 150 microns worth of design margin on the table that you don't need, right? And in the case of overhang, what does that mean? You can essentially reduce your overhang by 150 micron and squeeze more energy into your cell, add more cathode into your system. And so for 2170, about 150 microns of overhang means a 0.2% in energy density that you could gain back. And for a 10 gigawatt hour factory, that means that you can have an additional revenue, in terms of dollar per kilowatt hour, of about 1.6 million per year. And I think the key message here, this is just one example. When you're scanning your entire cell and you're able to build those reliable sort of distributions of your design because you're scanning so many cells per day, you can find those pockets of opportunities throughout your design to essentially squeeze more juice out of your factory while still maintaining your sort of quality level that's required by you and your customers. And so because this is just an example, we estimate that when you scan your entire cell and you look for those optimizations, you can eke out about 10 millions a year in additional value, and it could be cost saved or improved performance, so additional revenue.
Wow. So here we start off with a little orientation on the cost and performance and quality, and one example was a possible trade-off was design margin, and here we conclude with it as a concrete example. So I think we had a wonderful conversation, linking technology, hardware, software together with value creation, and now we can respond to some questions. One that we have received, this one will go to you, Eric, and that is regarding data and how. So obviously there, this is high resolution imaging. So how do you manage the data? How much data do you need to manage?
Yeah, and so data is a big challenge, right? And so I talked about bottleneck at the beginning of this presentation, and the X-ray source brightness is a bottleneck that you are removing here. The overall automation, loading, unloading, putting this source into a very fast system is another bottleneck. But what we learn is data management is a big bottleneck. And it is also even for conventional CT scanner, but even more so for this type of Superscanner technology. We're talking about terabytes per minute, right? And so this is kind of a crazy amount of data that you only hear typically in sort of microservices that are spread out across millions of users in sort of a web application. But here, those terabytes of data are produced at the edge in a single point, right, in the factory. And so if you don't have the right software solution to ingest, process, store, and then serve that data to your customer, you can't really extract any value out of this technology. And so terabytes per data, at Glimpse, we do a lot of advanced compression where we reduce the size of the data by orders of magnitude without losing information, valuable information. And we also help essentially the user consume information from that raw data in a way where you can draw a conclusion in a few seconds, right? Because obviously you cannot review every single scan, which is dozens of gigabytes every few seconds with humans. So you need sort of high performance processing, and you need computer vision to extract that information. So that's why we specialize at Glimpse. And it really has been a very nice synergy between Excillum, because you can think of Excillum as producing an enormous amount of photons, right, per unit of time. And you can think of VisiConsult as converting that photon into bits, and then Glimpse converting bits into sort of value for the end user.
Wow, nice linkage and summary, Eric. Another question from a cell maker is, how would I integrate the Superscanner or the VCB2 with my line?
Yeah, okay, I will take this question, I believe. So so here we talk about cylindrical cells. So when you look at cylindrical cells in the factory world, there are typical two ways of getting the cells transported to the factory lines. Either they're using some kind of pucks where individual cells are transported in a very high speed through the factories, and or in a certain other process, the cells are put in trays of 60, 80, 100 cells at once. And these cells then has to be moved in front of our machine, and the rest is just simple automation robotics. So our machine is designed that we can take it either from the pucks or from the trays with robots, single robots, dual robots, to accommodate also the required speed requirements from our customers. So it's fully designed for all kinds of ways of bringing the cells to our machine.
That sounds like an interesting and a fascinating discussion to have with the line owner, see how it best integrates. Thank you. So then I have one question, which I think is for myself, and that is, what about the reliability and the maintenance frequency of the source? So to start off with, we've designed the metal jet sources with reliability in mind. So that's from the beginning, and then we run lifetime tests for a year at the end, and we calculate MTBF numbers and reduce failure modes over that time. So that's the baseline. Then when it comes to maintenance, it's designed for once a year maintenance, and this is special for an open tube, because this includes the cathode change. So a normal message is 1 shift a year is required for doing the expected maintenance. I have one more question here that is, I think, for Eric, and it's about the performance of the algorithms in your software. What do you say about those?
Right. So it's a bit of a hard question to answer in the vacuum. It depends on the image quality, depends on which feature we're extracting, depends on a lot of things. But just to give order of magnitude here, the Superscanner will produce the order of a few thousands to a few tens of thousands of scans per day, right? So this is kind of the level of performance that you need to achieve. You need to deploy algorithms that don't produce too many errors per day or even per week, right? I think one thing we've focused very deeply on at Glimpse is the ability for the user to recover from any potential errors, either in term, because the error is driven by the image quality that's been degraded, or because our algorithms have gotten something wrong, right? And that will always happen. I think computer vision algorithm that never make mistakes doesn't exist and will never exist. And so the name of the game is really to enable the user to smoothly and elegantly recover from a potential mistake. And so that's why we've deployed those overlays, right, where you can very quickly go from a data point that might be an outlier to the corresponding features that created that data point. And maybe you're looking at a real outlier and you need to react very quickly in your factory, or maybe you're looking at those mistakes from the computer vision algorithms, and then obviously, we constantly take that data as feedback and then improve the performance of the algorithm. So I would say, in terms of performance, we work together with the customer. That's a discussion that we have with them. It depends on the feature that they're trying to extract, and then we make sure that it's very little maintenance. And when there is an error, which we try and make as rare as possible, the user isn't looking at sort of a black box, or an Excel sheet with just data points or measurements in there, right? They're interacting with a tool from which they can draw their own conclusion as to whether there's an issue in their factory or it's a red herring.
Thanks for sharing that reasoning. So I think with this one, we are about conclusion. So I guess we say thank you for listening in, and see you somewhere around.
Sounds great. Thanks for the discussion.
Thank you for the discussion. Thank you.